Welcome everyone to the Amazon ML Summer School. And in this session, we'll be covering causal inference. And this will be the part one for causal inference. And there will be two more parts, part two and part three. So we will learn about why causal inference is important, and we will discuss the foundations, formalisms, and the necessary notations and foundations to be able to understand why do we at all need to understand causal inference, and also learn about how to apply it in our practical applications. So in this part one of the module, we will learn about the motivation and framing, that why causality matters at all. So, in my understanding, causality is one of the understudied aspects of modern machine learning, whereas it has huge implications in decision making and interpretation of models and results. So that's why it's very important that we understand causality and causal inference in quite detail. So next we will understand about how causation is different from correlation, and how conflating these two might very easily lead us to draw wrong conclusions. We will learn about two frameworks for doing causal inference. So these will be formalisms, which will allow us to perform causal inference, and later on will help us build models based on these formalisms. So there are two formalisms differing in how, like slightly in philosophical way, and also what exact assumptions are they making, and how are they constructing the problem of causal inference. So the models that we would build would rely on either one of these two, or sometimes they are like exactly equivalent. Then we will learn about probabilistic graphical models and a very important theorem called deseparation theorem, which is about conditional independence in graphical models. We'll understand that how that is a very core concept of causality. We will learn a technique called do calculus, which will allow us to understand that when we can calculate causal effects and what do they exactly mean. And finally, we will understand about randomized control trials, which are gold standards in industry and also in academia for understanding the relationship between a cause and an outcome. So, to understand, so let's say the first aspect would be trying to convince you that why causal inference is important at all, and this is not just a academic exercise that we need to do. So, if you have ever built a model that has worked very well in offline evaluation, but it has failed when you have deployed, or like when you have deployed, the performance is, maybe it has not completely failed, but the performance is like very different from what you had observed in the offline data. So then that is the very at the core of those kind of problems is the fact that we are trying to do inference on a different type of a data distribution. And the correlations that we had learned in the training data may or may not hold very well when we are performing the inference in a production setup. So, and it's just not a problem about like lack of data or anything. So this can happen even if you're training models on huge amounts of data. So that is one like very practical aspect where we would need to understand why this has happened, and also preemptively understand that whether this can actually happen for some of our models. So let's understand a bit more about like what exactly do we mean by the relationship between cause and an outcome. So let's say we have a variable x on which we can choose to intervene. That is, we can set the value of x. So what I mean by intervene is that we are forcibly setting the value of x and not letting it vary naturally, right? So one practical example of this is when price changes are done for a product. So one aspect can be that the seller, like in an e-commerce platform, they could have set some natural price, or maybe whatever is the standard for that brand. So the price is set according to that. But what the seller can also do is they can intervene on the price, and on the platform they can choose to, let's say, offer a discount or deal, and that would effectively lower the price. So that's what is we are calling as an intervention. So in this example, like, so let's say x can be the price and y can be the like an outcome, which can be a sales or something. So similarly, like another example can be the a drug which is administered to a patient. So x can be an administration of a drug, or it can also be a choice of administration between drug A and drug B. And then the outcome y can be whether the patient recovered, or like what was the rate of recovery, like what if this is a pain reduction medicine, let's say what's the reduction in pain levels and so on. So that can be the outcome. And so now let's understand, like, what does p of y given x, and we also have a new notation, like say p of y do x. So on the left, we have p of y given x. So this is what we would learn from purely a supervised model. So this is the observed data distribution of the outcome given the features. On the right, we have p of y given do x. So this is what is called in a causal inference literature the Pearl's do operator. So it represents the distribution of y when we physically force x to take a particular value, regardless of what would have happened naturally. So again, like in the pricing example, like here it can mean, like, let's say giving a deal or discount where the price is now forcibly reduced, right? And now it has taken a lower value. So these two quantities are fundamentally different, and confusing them is a source of an enormous error, that we can make while understanding the relationship between x and y. So coming to like the hospital example, suppose like there is a hospital administrator who is looking at let's say health records. So the administrator might notice that patients who are prescribed drug A have lower readmission rates than patients who were on given drug B. So here the outcome we are measuring is, let's say, readmission rates, like whether the patient got well and whether he didn't get well and then they had to be readmitted. So the conditional model P of readmission, the Y given drug A, let's say hypothetically is lower than the conditional the probability of redemption given drug B. So here we are talking about the P of Y given X. So would that always mean that drug A is better? Um, so that's not necessarily true, because what could have happened is that drug A might have been administered to patients who were not so sick. So their severity of the disease would have been low, possibly. And drug B would have been given to patients, could have been given to patients for whom the severity was more. So although the observed uh, uh, probability of readmission given drug A is better than the if we just compare the observed distribution than drug B. But there is also an effect that drug A was systematically given to a different type of patients than what it was given to drug B. So just observing this like condition probability, and if we just say that drug A is better than drug B for all patients, that actually may be a wrong conclusion, because maybe B had improved the outcome for the more critical patients. So although like the readmission rates were higher, like the relative improvement that it had achieved, like even while dealing with like more difficult cases, that could have been better. So like the final kind of a conclusion maybe can be a hybrid thing, that A may be working for some cohort of patients and B might be working for some other cohort of patients. But just looking at the observed distribution of y given x, it might lead to a wrong conclusion. So that's why it's important to understand that that the observed data distribution can be very misleading if it is not correctly representing p of y do x, and if it is actually representing p of y given x. And like a lot of this part and the following parts will be about understanding, like given observed data, how do we estimate p of y given do x? So that's what we want to understand, right? That for each patient, if I had to do like A versus B, like irrespective of whether they're like very sick or not so sick, what would be the observed outcome? So, um, like a so at this point, I think it's important to understand what is the fundamental difference between supervised learning, causal inference, and another related line of like a very broad topic in machine learning called reinforcement learning. So apparently, like all these three can help us build models which can allow us to take some decisions, that let's say a price needs to be increased or a drug needs to be administered, and to which patients, in which quantity, and so on. But like for a particular problem, which type of a model or like a technology is helpful, and why that should be used, and like what are the fundamental differences between these three. So that's like very important to understand. So the learning objective of supervised learning is like beautifully simple. So it just finds a function f which minimizes an expected loss under the observed data distribution p. And we make a key assumption here that the training data is drawn IID from P, and that like now once we have trained such a model by minimizing such a loss function, then we assume that at the deployment time or the inference time, the distribution of the data that is coming in remains same as P. So here, like there is fundamentally no notion of taking an action, no notion of an intervention, or no notion of a counterfactual. So what does a counterfactual mean? So counterfactual means that for a particular individual, like when we are assigning him a particular treatment, say a drug, we can only observe the effect under one type of a treatment. Okay, and let's say there are, because simultaneously we can't give them like more treatments. So like assuming there's just one the individual is just suffering from one disease, so then sort of one treatment is given at a time. And if we are giving them like simultaneous treatments, that's also a different thing. But counterfactual means that we are giving an individual one treatment and then observing the effect. And the other treatments are sort of the effect of other treatments, or the outcome in the if the individual would have been given other treatments, that is not observed. So coming back to the supervised model, supervised learning. So what this model simply asks is that given the features X, what is the best fit for, or how can I get a function f which will provide me a best fit in the sense of minimizing this loss over the observed data. And now if the model is trained on this distribution P, and if the world also, like that inference time, it follows the same distribution P, then there is no problem. But if the distribution sort of changes, then this the learn function f was no longer optimal. And that's one of the you know that's why we sort of need this do kind of an operation, that if we are, so by intervening we are making a change in the distribution. And so that's sort of the where supervised learning sort of hits its limit, and then we need like more advanced techniques to learn that how do we have a function which is able to not only learn this, but also say that if there was an intervention, then what would have been the outcome. And um, so the quantity, like to more formalize, let's say T is a treatment and T can take two values, then like a quantity of interest is called treatment effect. And it is defined as the difference between the expectation of the outcome given one tree, like the tree being one, and the expectation of the outcome given t equals 0. And like there are many variations, but the idea here is that we are comparing two levels of the treatment. And depending on the problem, these levels can mean different things. So t equals 0 can means like absence of a medication, and t equals 1 can mean presence of a medication. T equals 0 means, let's say, can be an absence of a deal, and t equals 1 can mean a presence of some form of a deal or discount. And it doesn't need to be that the t has to be like just 0 or 1. So this is when it is binary, then we have a very clean definition of what is the treatment effect. But in general, t can be like continuous, high dimensional, take multiple values, and so on. And so this particular target uh, or this quantity that we have on the screen is called the treatment effect. And as we were discussing, this is not just a prediction. This is the uh, expectation under an intervention. So that's the most important thing to understand here. So, like an example that we have on the screen, that let's say, does a new blood pressure medication reduce the stroke risk? So, here the treatment is the new blood pressure medication, and the so what would t equals 0 mean? So t equals 0 can mean like either like having no medication, or it can also mean like having some baseline medication, like whatever was the incumbent existing medication. And t equals 1 means administering the new medication, and then y would mean the stroke risk. And then so we have the definition of treatment effect here. And like a related area where we want to also understand the effect or consequence of taking actions is reinforcement learning, where so the setup is sequential in that case, as opposed to IID, as we were seeing in causal inference or supervised learning. So here, the decision, the for a patient, or we would sort of see the sequence of outcomes. So we would administer a drug and then see the outcome, and then choose to revise it, increase the dosage, and so on. So the main fundamental difference between this and causal inference is that the data here is not IID. In particular, it is very likely that the data for a sequence is correlated, because the states are that's how the states are transitioning. So um, yeah, so that's basically the uh, core of reinforcement learning. And sort of we have a slide where we will summarize the difference between supervised ML, causal inference, and RL. So firstly, on data, In supervised machine learning, we will deal with IID samples of data coming from some distribution. And I think our assumption is that like the data on which we train and the data on which we will perform the inference can be a production setup or just be a test. So they are same as the training data distribution. So if the training data distribution is different from the test, then the results can be like quite different and like difficult to interpret, and the performance can be quite different and often worse. So that's in terms of data for supervised ML. For causal inference, the data is observational data. So it is also IID, but it is at the it is also observational. What that means is, although the question that it is asking that it is a question about intervention, the data is observational. So let's say in a smoking kind of an example, so let's say we want to understand what is the effect of smoking on weight gain. And in this case, let's say if we had to conduct or perform an estimation of this, we can't go and say to individuals to, change the like randomly change that treatment assignment, right? So in many cases, it is unethical or impossible or too costly to actually do like a randomization that for each individual we cannot say to ask them to change the treatment. So in that sense, the data is observational for causal inference. The targets that we have for supervised ML is about understanding the joint distribution of P of y and x, and also often we just need the mean or expectation. And for causal inference, it is about understanding the distribution of y given the intervention, the do of x. And for reinforcement learning, um, the target is often the value or the let's say so often we are interested in maximizing the total return over a trajectory. So that's a difference in how or what is our main quantity of interest in these three problems. And for in particular for RL, the data is not necessarily IID, and they are often episodes or trajectories. And within an episode and trajectory, the data points are not IID, and in particular, they are very likely to be correlated because they're transitioning from one state to the other. So actions, rewards, and states are in particular very likely to be correlated. And the question that just to summarize, the fundamental question that supervised ML asks is like given X, what will Y be? The question for causal inference is that if we intervene on X or intervene on T, what would Y be? And for RL, it is that which sequence of actions is best for to take to achieve a particular maximization of a value. In this case, it's the return, like often for classical RL. So in practice, like all these three are important and have their own place. But it's important to understand that, like at which setup, which type of problems, do we apply which one. So now let's have a short quiz where we will go over three statements and understand that which statement is about causation and which statement is about correlation. So the first statement is that countries spending more on healthcare have a higher life expectancy. So what do you think? Is it a causal statement that spending more on healthcare would lead to higher life expectancy, like if it could be framed in that way? The second statement is that in a randomized control trial, patients receiving the new antibiotic cleared the infection 2 days faster. Um, so, yeah, this is pretty much self-explanatory. And the third statement is that factories that adopted predictive maintenance had 15% fewer breakdowns last year. So now let's think about the three statements carefully, right? So if we go to the first one, uh, so the countries that spend more on healthcare are also typically the countries that are wealthier. And the GDP confounds both healthcare spending and life expectancy. So it can, like, you know, so wealthier countries can afford, let's say, better nutrition, better standard of living, education, and all of that can improve longevity or high life expectancy. So just from the like the wealthier countries can afford better nutrition, sanitation, education, better standard of living, and all these can improve longevity or lead to a higher life expectancy. So just by this statement, we can't say that spending more, or rather, without more analysis, we cannot say that spending more on healthcare does improve life expectancy. So if this statement has to be made, like, it needs more evidence by removing all these confounding factors, right? So the next statement: in a randomized controlled trial, patients are, randomly assigned. So what this means is the groups across which we are comparing, they are very comparable. And so one group got the new antibiotic and the other group was continuing with the old antibiotic. And then because they were very comparable, and then as such, because it's and the assignment is random, there is sort of no confounding effect by definition of the randomness. So this uh, you know so this means that if there is an effect due to the new drug, then this control trial is correctly sort of identifying it. And the final one is, little bit more ambiguous. So factories that adopted predictive maintenance likely did so because they were more technologically sophisticated and better managed, and possibly had higher budgets, and were already had maybe a culture of doing this maintenance, and they had like an improvement trend, possibly. So they were probably already going to have fewer breakdowns because of their how they have behaved or performed in the past. So however, it could also happen that because they did the predictive maintenance, the breakdowns were lower, right? So again, uh, the point I'm trying to convey here is that there are other factors at play, and depending on what those factors are, it could be that those factors are the actual ones which is leading to like an incorrect conclusion. So let's say the company was better managed, had larger budgets, like had better machinery at the first place itself, which led to a lower breakdown. Or it could be that that predictive maintenance actually had an effect. So while thinking about these kind of problems, you have to understand that, like, are we looking at all the right variables, and do we know the right relationships between them before we conclude on the effect of one or the other, or one on the other. So Yeah, I mean, I think we discussed the answer sort of. So next we will learn about some very important concepts called potential outcomes, graphical models, dissipation theorem, like a machinery called do calculus, and randomized control trials. This particular slide makes the correlation causation distinction very clear through two classic examples. On the left, we have the firefighter paradox. If we plot the number of firefighters deployed against property damage across a set of fires, we get a positive strong correlation. More firefighters observed, more damage. A naive analyst might conclude that firefighters cause property damage and recommend sending fewer firefighters. Obviously, that is absurd. The confounder here is the fire severity. The larger, more severe fires cause both more firefighters to be deployed and more property damage. The correlation between firefighters and damage is entirely spurious, driven by this common confounder. If we were to actually send fewer fighters, damage would increase, not decrease, obviously. The interventional effect is the opposite of what is the observational correlation. So this is how badly correlation can mislead us. On the right hand side, we have another classic example of Simpson's paradox. Hospital A has 70% aggregate recovery rate. Hospital B has 80%. Hospital B looks better in a marginal sense. But when we stratify uh, the patients by the severity of the cases, Hospital A has high recovery rates for both mild cases and for severe cases. So, how is this possible? Where we have contradictory observations if we look at the aggregate versus if we look at a stratified view. Because Hospital A is possibly a major trauma center that treats disproportionate share of severe cases. The severe cases have lower recovery rate regardless of the hospital. So Hospital A's aggregate is drawn down. So in this case, the confounding variable is the severity. So Simpson's paradox is not just academic; it constantly also shows up in real data. So when we are performing A/B experiments, clinical trials, and in various other experiments. So whenever we see that an aggregate observation is opposite to the direction, if we perform a stratification and then observe the direction, then that's an example of a Simpson's paradox, and that indicates that there are some confounding variables which are not properly accounted for when we are trying to understand the aggregate effect. So next we will learn about very important formalization called the potential outcome framework, which is due to Rubin. So this is also called the Rubin's causal framework and is one of the most widely used and applied framework for causal inference in economics, epidemiology, machine learning, and social sciences. Uh, for every individual, here we imagine two potential outcomes, yi of 1 if that individual I had received treatment, and yi 0, what would have happened to the outcome if they did not receive the treatment. The individual treatment effect is tau y, which is yi of 1 minus yi of 0. The problem, and this is called the fundamental problem of causal inference, is that we can never observe both the potential outcomes for the same individual. If patient I received the drug, we observe yi of 1, we never see what would have happened if the patient would not have been given drug, which is the yi of 0. Uh, the switching equation on the screen formalizes this. The observed outcome yi equals ti times yi of 1 plus 1 minus ti of y of 0. So we only see the potential outcome corresponding to the treatment that was actually received. And in that sense, the like all the causal inference problems can be so because we can't observe both yi1 and yi0 simultaneously, all the causal inference problems can be seen as missing data problem, right? Half the potential outcomes are missing, and we need assumptions to make correct imputations or correct corrections by controlling over the various factors. So um, yeah, so that's the potential outcomes framework. So next we would cover like a very brief background on probabilistic graphical models. A probabilistic graphical model, specifically a directed acyclic graph DAG, encodes a factorization of the joint distribution of a bunch of variables. The Markov property tells us that the joint probability of all the variables factorizes as a product of certain conditional distributions. These conditional distributions are where each variable is conditioned only on the parents in its graph. So this sort of a Markov property is like very powerful because it means that the graph structure can now be used to comment about conditional independence. And so in this diagram, the Z is a parent of both X and Y. X is also a parent of Y. The factorization of P of Z times P of X given Z times P of Y given X and Z. So that's how the joint distribution of P of X, Y, and Z is factorizing. So apart from the factorization, the causal sort of semantics are also very important here. So deleting an edge in this graph corresponds to the do operation graphically. So what we're meaning is, so let's say we sever an edge from Z to X. So what that means is that now X is being set or directly being intervened as opposed to being controlled by Z. So this, like when we are studying about a bunch of variables, so this, and if we can draw the relationship between them in this graphical form, then this graph also allows us to conclude about the conditional independence and like allows us to understand that which causal effects are at all identifiable and which are not identifiable. So we delve into the concept of conditional independence a bit more in the context of this graph. So we call like two variables x and y conditionally independent given another variable z if and only if the joint distribution of x and y given z factorizes in the form of the distribution of x given z and distribution of y given z. So this is a key. So basically, if we had to say it more plainly, once we know Z, learning X tells us nothing new about Y. So this is a key concept that tells us how to read the causal graphs that we were seeing previously. So there are exactly three ways in which the two variables can be connected to a third variable. And like each of these three types of connections have a different conditional independence pattern. So first we will look at something called a fork, where Z causes both X and Y. Without conditioning, like without any type of conditioning, X and Y are dependent because they share a common cause Z. But if we condition on Z, the path is blocked and now X becomes independent of Y. So the intuition here is that once you know the common cause, the two effects are unrelated. So in the GDP, the healthcare spending and the life expectancy example that we were seeing. So we also saw that, let's say the how wealthy a country is, let's say GDP, can cause increase in healthcare spending, but can also have an influence on life expectancy. But once we control for this GDP, the spurious correlation between spending and longevity or life expectancy weakens or can completely disappear. So that's why, controlling or conditioning on the Z, in this case, the GDP, is important to truly understand the effect or the relationship between intervening on X, how would it lead to a change in Y. So in the uh, second graph, which is called a chain, X causes M and that M causes Y. Without conditioning, X and Y are dependent because information flows through M. But if we condition on M, the path is blocked. So again, here the intuition is that once we know, so M is a mediator in this case. And once we know the mediator, the upstream tells us nothing additional about the downstream effect, right? So like the full effect of X is through M. So once we know M, then, we don't need to additionally know about X to, infer anything about Y. And the third and the most counterintuitive is the collider, where X and Y, they both cause some variable C. So now without conditioning, X and Y are independent because there is no open path between them. But if we condition on C, then we open a path and X and Y become dependent. So as an example, this is also called a collider bias. And suppose that both luck, as an example, like let's say luck and talent independently cause someone to be hired. Now, among the hired people, those who got in with less luck must have more talent. Conditioning on the collider, which is being hired variable, creates a negative correlation between talent and luck that does not exist in general. So that's sort of like a selection bias that you're introducing by conditioning on the collider variable. So it's very important to sort of understand these three patterns, as any complex graph or complex DAG can be broken down into a combination of just these three patterns, repeating in different ways across the graph. So next, we will learn about a very important theorem called the deseparation theorem, which is central to understanding about conditional independence in DAGs. So deseparation theorem allows us to build an algorithm to understand conditional independence directly given the graph structure without needing to do probability or conditional distribution manipulations or calculations rather. So here's the definition, right? So a path between x and y is blocked by a set of variables z if it contains either a non-collider that is in Z, which blocks the information, or a collider whose descendants are all outside Z, which leaves the collider closed. So X and Y are deseparated by Z if every path between them is blocked. So this was a key theorem proved by Pearl and Wama in 1988. And it says that deseparation is sound and complete. So what does soundness mean? So soundness means that if x and y are deseparated by z in the graph, then x and y are conditionally independent given z in every distribution compatible with this graph. And completeness means that if x and y are not deseparated, then there exists at least one distribution in which they are dependent. right? So it's sort of like a statement about so because we are dealing with just a graph, but we're not saying that okay, what's a distribution? So this statement is also about that if such a graph exists, then there exist such distributions on which for which they will be rendered dependent. So why does this notion matter to causal inference? Because deseparation tells us exactly which variables we need to condition on to be able to identify a causal effect. So we will shortly learn about a criteria called a backdoor criteria, where we will see that finding a set of variables z which blocks all backdoor path from a treatment to outcome without including any descendant of the outcome, that sort of leads to conditional independence. And So as such, we don't need to directly use this theorem, but we will sort of learn more direct ways of understanding, when causal effects are identifiable and what variables to condition on. But still, this remains at the heart of causal inference, that because this theorem allows us to understand like when variables are conditionally independent and when they are not. So we will also learn one type of machinery called do calculus, and it provides rules for manipulating expressions involving the do operator and reduce them to purely observational quantities when the causal effect is identifiable. So we don't necessarily need to directly apply these often because there are like algorithmic ways in which if like given a particular graph allows us to identify a causal effect, then the algorithms would sort of uh, using the rules of this do calculus allow us to derive an expression from which, using observed data, we would be able to derive the causal estimates purely from observational data. So as such, I'm not going to go deep into the rules, but just this is more for a reference that these rule exists, and these rules can be converted to an algorithm which will tell you okay, like is a causal, given a graph, is a causal effect we can estimate it in an unbiased way or not. So rather more important is two criterias called backdoor and front door criteria. And these are much more commonly used in practice. So this is where you might want, find more practical use. So the backdoor criteria is one of the most commonly used in practice. So what it says is that if we can find a set of variables z that blocks all backdoor paths from x to y, meaning that and z does not contain any descendant of x, then the causal effect is identified by the backdoor adjustment formula that we see on the left. The formula says P of y given do x equals the sum over like marginalizing over z of P of y given x and z times P of z equals z. So in other words, we basically condition or stratify by z, and then within each strata we understand the joint distribution of x and y, and then aggregate according to that strata proportions, and that gives us the interventional effect of x on y. So you will later see like some techniques called propensity matching, which is sort of like using this core idea. And we also have another criteria called the front door adjustment, which is less common but also powerful because it works even when we have unobserved confounding between x and y. So it requires a mediator M such that X affects M only through M, X affects Y only through M. And there is no direct X to Y path, not through M. And there is no unblocked backdoor path from X to M. So again, under this situation, the front door adjustment gives us a formula to be able to calculate the interventional effect using observational distributions. So yeah, and finally we will cover like having understood the conditional independence notion. So what's the gold standard for causal inference? Because one aspect is that we saw that yes, using the front door and backdoor criteria, we can derive expressions for obtaining estimates of interventional effect from observational data. But like, what can we do better than observational data? And an RCT or the randomized control trial is an answer to that. So randomization guarantees that the treatment assignment T is independent of all potential outcomes, both y of 0 and y of 1. And in graphical terms, randomization means removing all incoming edges uh, to T. That means that there are no backdoor paths from T to Y. Every path from T to Y is a causal path, a front door path. Therefore, the average treatment effect is simply the difference in mean outcomes between treatment and control, and no adjustment is needed. So we don't need any assumptions about confounders, no identification problem is there. So that is why the formula looks so clean for a randomized controlled trial where we just can compare the outcomes of the two groups directly. But there are some potential challenges with RCTs in the sense that they are costly to run. They are sometimes non-ethical, like in the smoking example that we were seeing earlier. And we also have to ensure that whatever is the RCT population, like is it a good, like, or the set on which we are performing the RCT, is that entire set representative of the whole population or not? Because sometimes it can be difficult to do an RCT on the entire, like taking a representative sample from the entire population, and then there can be compliance challenges also in conducting RCTs. So, however, like nonetheless, like when we can actually conduct RCTs, like for example, AB experiments in industry, or like lots of medical trials which are conducted, so they do give the cleanest way and the most statistical power to perform inference about the treatment effect and give us a very conclusive answer. So with that, we conclude the part one, and in part two and three, you will learn more about techniques which build on these fundamental ideas of identifiability, conditional independence, treatment effect estimation, and then you will learn more specific machinery to build models around these to get different causal estimates.